You're going to take calculus, and you want to know, are you ready for it? Do you know the algebra that's needed? Well, this video is for you. I'm going to go over everything that I think you need to know specifically for calculus. I'm not going to go over all of algebra. There's far too much. I'm going to go over the things that will specifically be done in Calculus 1. These are the things that I have found that are often the reason people fail calculus, is because they don't know how to do these things. So if anything in this video gives you trouble, these are the things that you should review and learn how to do. If you understand every problem in this video, it is my personal opinion, disclaimer, no guarantee, but it's my personal opinion that you will be just fine when you take calculus. So let's go on to the first topic. The first topic is order of operations. It isn't specifically algebra, but it is very much important. Often I just call this PEMDAS, or maybe please excuse my dear Aunt Sally. Basically, this just tells you what order do we want to do things in. For a quick example, let's say we do 5 plus 2 times 3 squared minus 1, like that. If we want to simplify this, we have to start with the P. That's P for PEMDAS, or P for parentheses, sorry. So we look at this and say we better do these parentheses first. And inside that parenthesis, we better do our own PEMDAS. It's going to have a separate PEMDAS for the parentheses. We start over and say, are there any parentheses in that 3 squared minus 1? Well, no, there are no parentheses, but you could have a situation where you have a parentheses inside of a parenthesis. So watch out for that. But in this case, we don't have it. So we go to the next thing. That's going to be the E for the exponents. And we do have an exponent, so 3 squared, that's 9. And then we still have our minus 1. We go on. M and D. That's multiplication and division is the next thing you do. Now these are at the same level. So remember, if there's things that are at the same level and you're not sure what to do first, go from left to right. But in this case, there are no multiplication or division. So we'll go on to the next step, which is addition and subtraction. Again, these are at the same level. We really could have called this PEDMOS, or let's see, PEDMSA, I don't know. But PEMDAS seems to roll off the tongue. So just keep in mind those are at the same level. So what I'm going to do now is just say 9 minus 1 is 8. So that is the solution to just the parentheses. So now we have to go back to our original PEMDAS at the beginning here. We have 5 plus 2 times that parenthesis, which ended up giving us 8. So in this one, all we've done is the P. We have dealt with only the parentheses. And now we're ready to go on to the exponents. There aren't any. Multiplication and division together. That's going to be multiplication here. So 2 times 8 is 16. So we do 5 plus 16. Now we're done with multiplication and division. And now we're ready for the addition and subtraction. So for the addition and subtraction, that's going to just be 21. So that's our final answer. We went through PEMDAS, and notice we had to do it twice. You really have to do it once for each time in the parentheses. For each parenthesis, you have to do it an extra time. Okay, so let's take a look at one more problem now. Here we have 12 divided by 2 squared plus 5 times 3. So we'll start off with PEMDAS again. So we do the parentheses. So here's a parenthesis right there. It actually doesn't matter. We don't really need these parentheses, but they're there, so let's do them. So inside that parenthesis, all we have is an exponent, so that's just going to be 2 squared is 4. So we have 12 divided by that 4 we computed, plus 5 times 3. So we're done with the parenthesis. Now we go to the exponent. Well, there are no exponents anymore, right? We got rid of that. And that's why we really didn't need the parenthesis here. We would have done it anyways. But now we move on to multiplication and division. So multiplication and division, like I said before, are at the same level. But there's only one of them, so it's just division. So we do that. 12 divided by 4 is 3. And then we still add, oh wait, we have another one. 5 times 3 is 15. So we're done with the multiplication and division. We're ready just for the final part, the addition subtraction, which is 3 plus 15 gives us 18. So that's our answer. All right, let's do one more of these before we conclude. Here we have 6 squared divided by 3 in parentheses, plus 5 times 4 minus 1. So in this case, We start off again with parentheses, so we'll do the parentheses first. We have two sets of parentheses, so we'll have to do its own PEMDAS for each one. We'll start with this one. We have 6 squared divided by 3. There's no parentheses inside of that, so we can go on to the exponent, which is 6 squared, so that's 36 divided by 3. And then we go on to multiplication and division. Well, there's division, so 36 divided by 3 is 12. So we've done that parenthesis. But we have another parenthesis, so let's do this one. Well, here, it's just 4 minus 1. You could think of it as going through the whole thing, but if there's only one operation, you really can just do that one operation, which is 4 minus 1 is 3. So now we have 12 plus 5 times 3. We're done with the parenthesis for the first part. We're done with all the exponents. There aren't any left. And then we have multiplication and division to do. So we have this 15, right? 5 times 3 is 15. So we have 12 plus 15. And then we just have our addition left to give us, add those together to get 27. So we end up with 27. So this is my review of PEMDAS, also known as order of operations. The next topic I want to talk about is basic equations. By that I mean, can you solve an equation? If we have an x in an equation, can we solve for it? So say we have, for example, 3x plus 6 is equal to 2x minus 8. We want to find the one unique x that will make this equation true. There's only one of them, and we want to know what is that. To do that, we need to do whatever we want to this equation. We can do anything we want as long as we do it to both sides. And we want to end up with x all by itself on one side of the equation. So what I like to do is I like to get rid of simplify both sides first, which this is already done, and then just move everything to one side. Specifically, write x only one time. So this 3x and 2x, I want to move the 2x to the other side. I could move the 3x to the other side instead, move it to the right, but then I'd end up with a negative number and I just don't want to deal with that. But it does work. If you prefer that, go ahead. So to move something to the other side, you just have to identify the opposite. So that 2x is added to the equation. So we're going to subtract it from both sides. Oftentimes I see people writing stuff like this, minus 2x and minus 2x. I don't really like that notation, but if you like it, go ahead. I probably won't show it again. We have 3x minus 2x gives us just simply 1x. We still have our plus 6. And then on the other side, 2x minus 2x goes away. And that's how we moved it to the other side. And then we just have our minus 8. Don't drop that negative. Negatives are very, very much important. So now, to get x all by itself again, we just have to say, well, what's being done to x? In this case, we're adding 6. So just like before, let's subtract it to move it to the other side. So I'm going to subtract 6 from both sides. So on the left side, the 6 and 6 cancel away. We did that by design. So when we just get x equals, well, we have the negative 8 minus 6, which gives us negative 14. So we got x all by itself on one side of the equation, and now it equals negative 14. If you were to plug that back into the equation, which we don't really have to do, we have our answer. It's negative 14. But you know, in math, it's a very good idea to double check yourself. So let's do that here. We would have 3 times negative 14 plus 6 is equal to 2 times that negative 14 minus 8. So I don't know, what is 3 times 14? I'm going to need my calculator for that. But that's going to end up with negative 42 plus 6. Is that equal to 14 times 2 is negative 28 minus 8. So negative 42 plus 6, that's the same thing as 6 minus 42, which is negative 36. And we have negative 28 minus 8. Hey, that's negative 36. So if you end up with something like this, you know you got it right. So our answer is, in fact, negative 14, and we've double-checked to make sure that we are correct. Let's try another problem, make sure we've got this. Here we have x plus 1 squared minus 4 is equal to 0. Now in this case, I'm actually not going to try and solve for x. I'm actually going to try and solve for x plus 1. So I'm going to treat that x plus 1 as if it's all just one entity, one variable. So if I were to solve for this thing, I would want to get rid of this 4 first. And by the way, This is just a little bit of a trick. It doesn't work in all cases, but I think of equations as PEMDAS backwards. You almost always want to start from getting rid of the addition and subtraction and do the parentheses last. So this is a great example of that. We want to get rid of the addition and subtraction first. And we'll do that by just adding 4 to both sides. So we get x plus 1 squared, because the 4 and negative 4 go away. And we added 4 to the other side to get 4 over here. We moved it to the other side by adding, which is the opposite of subtraction. And then if you think of it as PEMDAS, we look for multiplication. There isn't any. You look for exponents. Okay, let's get rid of that exponent. So we have x plus 1, if we take the square root of both sides, is going to be the square root of 4. Let's be careful here, right? Because if I take the square root of 4, you always have to do a plus or minus whenever you take a square root. That's true for any even root, in fact. If you take a square root, you have to have 2 possible options. So this is just plus or minus 2. So now I go on to x plus 1. Well, let's just subtract 1 to get x is equal to negative 1 plus or minus that 2 that we have. Now, if you're like me, I used to be confused with this plus or minus. I'd see teachers writing that, and I didn't really know what it meant. Well, this just means you have 2 choices. It is the same thing as writing, well, we have negative 1 plus 2, and we also have negative 1 minus 2. It's a way of just shortcut way of writing it. And so this gives us negative 1 plus 2 is 1, and negative 1 minus 2 is negative 3. So we have 2 possible choices. We have x all by itself on one side of the equation, but we have 2 answers. And in fact, anytime you have a quadratic, you're going to have 2 answers. Although it gets a little more complicated than that. Some are real, some are imaginary. I'm not going to worry about that too much here. And just like we always should do, we could check this and plug it in, see if it works. If I plugged in 1, I'd get 1 plus 1 is 2, squared is 4, minus 4 is 0. Great, it works. I'll let you double check the negative 3 if you'd like on your own. Let's take a look at one last problem for this. Oh, actually, we'll do a couple of these, but let's let's look at one more. Here, this is going to be a very short one, but I do think it's important to note. In this case, we have x minus 3 is equal to x plus 4. So if we just kind of blindly solve this like we would subtract an x to move it to the other side, and we'd move this to the other side as well. So x minus x gives us 0, and then 4 plus 3 is 7. So that's not good, right? 0 equals 7 as the solution. Well, that's clearly not true. So if you get something that's not true, that means the only way this thing can be correct is if 0 equals 7, which is clearly wrong. So this has no solution. So sometimes these equations have no solution. They could have infinitely many solutions. If you end up with something like 7 equals 7, that means there's an infinite number of solutions because any x that you choose where 7 equals 7 would be a solution. Well, obviously, no matter what x is, 7 always equals 7. So that would be all x. But in this example here, we had no solution because we ended up with 0 equals 7, which is just clearly false. All right, now we truly only have one problem left. Let me do this one, which I do think is very important for calculus. Let's do x minus 1 times x plus 1 is equal to 0. Now, I want to point out that there's a very, very, very useful formula you should definitely know, that if you have a times b equals 0, that means either a equals 0 or b equals 0. There's no other way that could happen. And that's what we're going to utilize here. We have a is x minus 1 and b is x plus 1. So either x minus 1 is equal to 0, or we could say that x plus 1 is equal to 0. There's no other way this could possibly work. So if you have an equation that's in a factored form like this, that's a great way to do this. Now, we will be talking about factoring later, but for now, let's not worry about that. So I'm just going to solve each of these equations separately. So x minus 1 equals 0, I'm just going to add 1 to get x equals 1. And then on the other one, we'll subtract 1 to get x equals negative 1. So those are our 2 solutions. For either one of those answers, this thing will be 0. All right, let's take a look at our next topic. Function notation is something that's very important in calculus. It's really just a notation. So really, you just have to make sure you understand what it means. It's not really any new math. It's just how we write and understand math. but we use it a large amount in calculus. So, for example, if I have something like f of x is equal to x squared plus 6, well, this is exactly the same thing as if I said y is equal to x squared plus 6. There's really no difference. The reason we like it in calculus is because this one gives you just a little bit more information. It tells you that x is the variable. But, I mean, you might say, well, don't we know x is the variable, right? We have x squared plus 6, right? Well, what if we had something like this? What if we said f of x is equal to x squared plus a? Well, which one is the true variable? It turns out that what we mean by this is x can change. Now, this might be a little confusing, and I wouldn't worry about this too much because you'll learn more about this in calculus. But x is the variable, meaning it can change. So given a scenario, x will change. Like if you were to throw a ball, time would change as you throw the ball, right? But this value here for a given scenario is the same. We call that a constant. So it's actually, while it is technically a variable, it's a constant variable that never changes. If you look at a situation where you throw a ball, like say I throw a ball from some height here, and it flies like this, as time goes on, we are changing that. So that would be the variable. But we throw it from a given height. I could call that height A, for example, and A would be constant. Throughout this entire time that I've thrown the ball, A doesn't change. It's the same, but time does change. So there's a little bit difference between an X variable and an A variable in this function notation. It's telling you that A or X is what changes. Whereas if I were to write f of A equals x squared plus A, that means a completely different thing. It tells me that x is actually constant. It's some variable, I don't know what it is, but whatever it is, it doesn't change, whereas a does. Now, I've kind of gone off on a tangent there. I apologize for that. Don't worry about all this stuff on this side too much because you will learn all about that in calculus. But getting back to the actual function notation, this f is just telling you what is there. Now, we could change it, right? Like if I were to give you like, what is f of, well, x is just a variable. You can replace it with anything you wanted. So like, what if I wanted to say, what is, given this f here, what is f of b? Well, f of b would just be replace x with b. So we'd have this x squared plus 6. I like to write it like this parenthesis first, just to show that, hey, we throw in anywhere we see that, anywhere you see an x, you throw in a b. So that is what function notation looks like. What is it? I could also say, well, what's f of 2? Well, that's just going to replace x with 2. That'd be 2 squared plus 6. Well, we know order of operations, so 2 squared is 4 plus 6 is 10. That is f of 2. In fact, we could plug in anything you wanted here. So one thing that we're often going to plug into calculus, sorry we're getting a little busy here, we'll finish this up very soon, is you might want to find what is f of x plus h. That comes up all the time in calculus, is finding f of x plus h. Well, it's no different. We just replace x with whatever's in that parenthesis. So we have x squared plus 6. So we just plug in this x plus h there. That is f of x plus h. And then you'd have to do some foiling for that and simplify. Okay, now that we have an explanation of what function notation looks like, let's do an example. Here we're given a function. We have x squared plus 2x minus 3. And we want to find this complicated looking thing. This is f of x plus h minus f of x over h. Now this is actually something you will, I pretty much guarantee you will be doing this in calculus. This is probably the number one reason why someone fails calculus is because they can't quite handle this algebra, this exact algebra we're seeing right here. So let's do it. So we need to take this one piece at a time. So first, let's find f of x plus h. So f of x plus h, just like we did before, that's going to be our x squared plus 2x minus 3. But inside of there, we'll plug in x plus h. Okay. So now we better simplify that down a little bit. So if we look at this first part here, that's going to be a squared. We have some x plus h times x plus h. We need to FOIL that out. So we'll have x plus h times x plus h. That gives us x squared plus an xh plus another hx, so there's actually two of them, plus h squared. So if you're not familiar with foiling, I'm not truly covering that here, but feel free to just Google that if you need more help. It's called FOIL. Take a look for that. But this part gives us that. Then we're going to distribute this 2 to this part. So we have a 2x plus 2h as well. And then, of course, we just have that minus 3. So that means that we have, let's see, f of x plus h is going to be, if we combine like terms, we have an x squared, and then we have a 2xh, and an h squared, and a 2x, and a 2h, and a minus 3. I guess we didn't combine any like terms because there weren't any, but that's okay. So then we subtract f of x now, right? This whole thing right here is just f of x plus h. So we'll subtract f of x. So that's going to be x squared plus 2x minus 3. Be very, very careful about this minus sign. People mess that up because make sure we have to distribute that minus to each part. So you want to be careful that you put those parentheses there. But then what I'm going to do is notice that we have an x squared minus, let's do this in another color here. We have an x squared minus another x squared. We have a 2x minus a 2x, and we have a negative 3 minus a negative 3. So drop that parenthesis there. Those just cancel each other out. So if I divide this by h, all we have is, let's see, we have the 2xh plus h squared plus 2h over h. Everything else went away. So now if I can continue simplifying this, we can factor out an h. We're left with 2x plus h plus 2. And there's still an h in there. The h's cancel, and we get 2x plus h plus 2. Great. So that is f of x plus h minus f of x all over h. Now, I'm not going to tell you what this means in a calculus perspective because, well, you'll learn all about that in calculus. Just know that you will be expected to be able to do these kinds of things in calculus. Now, because I think this is just insanely, insanely important, let's do one more example that's very similar to this one. But it's going to be a little bit simpler. Here we have basically the same question. We have f of x is equal to 2x plus 3, a different function, but we're still going to find f of x plus h minus f of x over h. So we'll start off again by just saying, what is f of x plus h? Well, we take the 2 times the x plus 3, but we replace x with x plus h. Now this one's going to be a little simpler because we don't have to square it. So we'll do 2x plus 2h when we distribute plus 3. That's it. Much more simple. So we'll take that 2x plus 2h plus 3, and we'll subtract the original f of x, which is 2x plus 3, and then divide by h. Now, just like before, we have some things that go away. That's 2x minus 2x goes away, and 3 minus 3 goes away. So we just have 2h is all that's left in the numerator. When we divide that by h, it cancels, and this is just 2. Now this is interesting because, now disclaimer here, if you don't want to learn any calculus, you could just drop this part, don't worry about it. But there is a direct relationship to this number of 2, which, if you remember, is the slope of a line. Now I will talk more about that slope of a line, but there is definitely a relationship, that there's a reason that we ended up with that slope of the line, and you'll learn all about that in calculus. But for now, I think that's all I want to teach about function notation. It is, I would say, the single most important topic you should learn before you take calculus. But let's go ahead and go now to the next topic. This topic is about factoring, because in calculus, you're going to often need to solve an equation which will require factoring. Also, you're going to have to compute something called a limit that will again require factoring, and I'm sure other reasons as well. So let me give you kind of my view of how you factor. You're going to go through an order and say, okay, the first thing I'm going to look for is a common factor, meaning what is just something you can pull out that's common to everything. That is always going to be what you want to look at first before you do anything else. I'll look at some examples in a bit, but next, let me go ahead and say the next thing I would check for is a formula. There aren't a whole lot of these. The only one really that I would say you definitely need to memorize before you go into calculus is the difference of two squareds formula. It's also a good idea to memorize a few other formulas like the sum of two cubes and the difference of two cubes, but they're nowhere near as important. And then the next thing I would say, if you can't find a formula, is what I call the double bubble. Now, this is actually what most people refer to when they think of factoring. This is where you draw those two parentheses, you find two numbers that multiply to give you something and add to give you something else. Well, we'll go over that in just a bit, but that's what I call the double bubble. And then if that fails, the next option I would check for is AC. Now, this AC method is one that I wish people taught more. It basically is what happens when double bubble fails, but you still have something that's factorable. Some teachers teach to just do guess and check, and I never like guess and check. So I'm going to show you a better way to factor using that. And then if that fails, you can still try grouping. Now, AC and grouping are kind of together. AC actually is a way to turn it into grouping. So I'm going to talk about those together. But these are the ways that we factor. So now we've talked about that. Let's look at some examples, and I'll try to do some of each of these. For our first example, let's look at 2x squared plus 4x and try and factor this. Now, this is a great example of a common factoring because you'll notice that 2x squared, well, if you factor that, find all the common factors, well, there's a 2 and an x and an x. Those are all the factors. For the second part, we have a 4, which is a 2 times 2, and an x. And so you'll notice there are some common things. There's a 2x, let's use a different color here, 2x in both of them. So since it's common in both, you can factor it out, which is actually just division. When you pull it out, divide each of these terms by whatever you pulled out. So the 2x squared divided by 2x is just an x left over. Or just look at, the one thing left over. And then when we take 4x and divide by that 2x that we're pulling out, well, we're left with just this one thing here, 2. So this thing factors by common factoring, which if you ask me is the easiest one. That's how I have it on first in the list. Always do it if you can. Is 2x times x plus 2. So we have now factored this, which is very useful, as I mentioned, for solving equations. Like if this were equal to 0, we would take it another step. And for that, there's another video about how to do that. But for now, we're done with that factoring. So let's take a look at another example. Here we have a quadratic, x squared minus x minus 2. Now, this looks like it kind of falls into the more classical what you picture when you learn factoring. It's basically something like this. But I would still look at it first and say, okay, can we do a common factor? And the answer to that is no, because the first term only has an x in it. Those are the only factors is x and x, but the last term doesn't have an x. So we can't do common factoring. But I still recommend that you look at it because it's very, very important and easy. The next step we look at is a formula. Well, I think the only one we can really talk about right now that we know is the difference of two squareds, and well, this is not the difference of two squareds. We will talk about that in a moment, but this is not just taking something squared minus something squared. So that brings us to double bubble, which I think we expected because this is a typical factoring thing. So we're going to end up with double bubble. So when you do the double bubble, you just put parenthesis, parenthesis, x and x. You always start off the same way. But then we want to find two numbers that multiply to give you 2 and add to give you 1. So what I like to do is just write the 2, and I like to ignore the negatives until the end. They are very important, but I'll ignore it until the end. And just think, okay, how can I multiply two numbers to get 2? Well, there's only one option, 1 and 2. And then after I figure that out, now I'm going to consider the negative and say, well, because this number is negative, two numbers that multiply together to get negative means only one of them is negative. So one of these two has to be negative, and which one will be determined by this sign here. Because when I add them together, I want to get -1, a negative. So let's make the bigger one negative. So we'll put the negative on the 2. So we found we want 1 and -2. So we just say +1 and -2. And that's it. Now, you might ask correctly, and if you don't know the answer to this, please pay attention because you should. You might ask, why did we do that? Why did we find two numbers that multiply to give you -2 and add to give you -1? Why would we care? And the answer to that is if we were to FOIL this out. So FOIL means let's do first, outside, inside, last. We're just going to simplify, basically, is what that is. So the first is x times x, that's x squared. And if we were to do the next part, that's x times negative 2, so minus 2x. And then the inside is 1 times x is plus 1x. And then the last is 1 times negative 2, so minus 2. Now if I simplify these, we have x squared. And then these two terms in the middle here are common terms. Negative 2 plus 1 is minus 1. And then minus 2. Now, if you look at what we did there, it should pop out, right? Why did we look for two numbers that multiply to give you negative 2? It's because in this blue one right here, we took 1 and negative 2, and that's where we got that 2. Also, why did we look for the numbers that add to give you a negative 1? That's because of this middle term here. We add the negative 2 plus the 1, and that's what gives us, in the end, this negative 1. So that gives you a little bit of why we do the double bubble the way we do. All right, let's take a look at another example. Here we have 6x squared plus x minus 1. Now you might think this looks like a double bubble. But let's start off and say, okay, common factoring, nope, that failed. Formula, nope, that failed. Double bubble. Double bubble, if you ask me, requires that you have x squared only has a 1 in front of it. So this 6 means we can't do the double bubble. Now here's where I might disagree with what your teacher taught you, because it is possible to go ahead and say, oh, well, let's take a guess and check approach and say, okay, how about 3x, 2x, 1, and 1? You can do a guess and check approach. But I never like guess and check in math. I will always try and find a way to avoid that. So I'm not even going to show that here. But if you want to do the guess and check approach, go ahead. But what I'm going to do is say double bubble has to have the leading coefficient here, a 1. So double bubble failed. That leads us to the AC method. Now the AC method basically is for things that you would think it's double bubble, but hey, the leading coefficient isn't 1. So what I'm going to do is I'm going to multiply A times C, thus the AC, right? Remember, if you have AX squared plus BX plus C, that's where the AC name comes from. I'm going to multiply A and C. So that gives me 6 times negative 1 is negative 6. Now I'm going to pretend for a minute that we did have a double bubble and we were going to factor x squared plus x minus 6. I just replaced this last number with this one. We're pretending this isn't quite right. Let's not really do that. But that's what we're going to be thinking of. So we want two numbers that multiply to give you negative 6 and add to give you 1. So that's going to be 3 and 2 that differ by 1. We have to have a negative for the negative 1, so one of them's negative. And they have to add to give you a positive number, so let's this time make the smaller number negative, so 3 and negative 2. Now, instead of doing the double bubble with that, though, we're going to take that information and do something different. We're going to take this thing, specifically the middle term, and change it. So we have 6x squared plus x. But if you remember, the 1 can be rewritten as 3 minus 2. So let's do that. We have 3x minus 2x. We broke it up in a very specific way to make this work, minus 1. We just replaced this x with 3x minus 2x. And we know that'll work because, hey, we looked for two numbers that makes that work. Now, let's do grouping. So I'm going to kind of teach grouping now, because grouping is where you basically probably have 4 terms, and you just take the first 2 and the last 2 completely separately. So I'm just going to factor the first 2. So we go back to the beginning of our factoring list and say, okay, can we factor out a common factor? And yes, we can. We can pull out a 3 and an x. We're left with a 2x out of the 6x squared. And, well, we pulled everything out of the 3x, so just plus 1. Then for the next part, here, let's be careful because we can pull out a negative. And I would advise, if you can pull out a negative, you should, if you see a negative in front of the highest power. So I'm going to pull out a negative, and that's really all I can pull out. But I have 2x and then a plus 1 because I pulled a negative out of both parts. Now here's where you hope you got lucky. If you were dealing with grouping, if you're dealing with AC, you should get this, otherwise you did something wrong, is that these two things should be the same. And if they are, well, let's just go ahead and do common factoring again. We can pull out that 2x plus 1 as if its own thing. And we're left with the 3x in the first part and a minus 1 in the last part. So now we have factored this. That is what I call AC factoring, which also incorporated knowing how to do grouping as well. Okay, I have one more example to do for factoring. Here we have something a little bit different than we've done in the last examples. We have x squared minus 4, and it's equal to 0. So because it's equal to 0, we want to take it a step further. We don't just want to factor, we want to solve. Now, I want to point out, you don't actually have to factor to solve this, right? You could just add 4, get x squared equals 4, so x is the square root of 4, so plus or minus 2. Done. Okay, but hey, we're trying to learn how to factor. So let's actually solve this by factoring instead. So let's undo that. And so if we're going to factor this, we start off again by common factoring. Always start with common. Well, it failed this time. It didn't work. And in most of my examples, common factoring doesn't really work. But please remember to do it because you might very well get to the point where you spend a lot of time trying to factor something that, well, could have just been common factoring. So we go on to the next one, which is a formula. Well, now we do have a formula because this is the difference of two squareds. We have something squared, x, minus something else squared, which is 2. So we can factor that. So that factors into x minus 2 times x plus 2. Now, if you don't know the difference of two squareds formula, I'll give it to you now. If you have a squared minus b squared, that will always factor into a minus b times a plus b. So in our case right here, a is x and b is 2. So we just have x minus 2 and x plus 2. And then that's equal to 0. We're done factoring. Well, we're not done solving it. We're not done with the problem, but we're done factoring. Now we just have to say, okay, well, the only way these can be equal to 0 is if this one's 0 or this one's 0. So if x minus 2 is equal to 0, we'll add 2 to get x equals 2. And if x plus 2 is equal to 0, we'll subtract 2 to get negative 2. Hey, that's the same thing we got before. Which is what's really nice about math is you can do it all sorts of different ways, and you should still get the same answer. If you don't, well, you made a mistake. All right. So that is all I have on factoring. But let's go ahead and go on to the next topic. The next topic I want to talk about is exponents. So exponents basically means how can we simplify some equations or expressions that have exponents. Now there's a few rules that we should know. For example, if I have x to the n raised to the m, that's equal to x to the n times m. That's a very important rule to remember. And another one very similar to that, but kind of opposite, is x to the n times x to the m. That's equal to x to the n plus m. So I remember this as if you have something to a power to another power, you multiply them. And if you have the two bases to different powers, you add the powers. These are two of the most important rules, and I'm going to add in a third, that if you have a negative power, it just means 1 over that x to the power. Now, there are other rules of exponents, but I am just covering the things that I think you really need to know before you take calculus. And I'd say these are the most important exponent rules. So let's go ahead and do an example of this. Here we have 2 cubed, and that's going to be squared. Now, I want to point out before we start, this is something that I was actually in calculus when I personally realized the error of my ways. This is not the same as 2 to the 3 squared. These are two completely different things. So be careful about that. These are not the same because this one is 2 to the 9th. And this one, as we'll talk about now, this is 2 to the 3 to the 2. Well, that's something to a power to another power. You multiply the powers, you get 2 to the 6th. So that is very different. These are not the same thing. Be very, very careful about that. I nearly failed my calculus class because of that. So let's go on to the next example. So this one is very, very similar to the last one, but I feel it's fairly quick and important. So we're going to have 2 to the power raised to another power. So we multiply the powers, and we get 2 to the 12th. All right, one more. So here we have x cubed y to the negative 1 over x to the negative 3. And let's just simplify this down. Let's drop all the negative powers and only write each variable once. So we have a choice in how we go about all of these problems. So one thing you might try and do is just write it without any negative powers first, because negative powers, if you ask me, are confusing. Now this rule right here directly says that if you have a negative power, it's the same as just dividing by it. But I'm going to take that a step further and say that this rule means that you can take a negative power and switch it freely between numerator and denominator if it's a negative power. So really, this y, I think of it as actually this y is in the denominator. Likewise, this x is actually in the numerator. So we have this x cubed that didn't get changed, and I'm going to take this x cubed here and move it to the numerator. Just change the sign. If you move it between numerator and denominator, you just change the sign. And then the y gets moved as well, so that one becomes just y to the first power is where that one went. So a negative power just means change where it's at. If it was in the numerator, put it in the denominator. If it was in the denominator, put it in the numerator. So now this y is as simplified as it's going to get. I'm not going to touch that. But we can simplify the x cubes. We have x cubed times x cubed. That's going to be this rule here. We have x to a power times x to another power. We're going to add the powers. So that's going to be x to the 3 plus 3 is 6 over y. So that's x to the 6th over y is our answer. That's as simplified as we can get. All right, let's look at another one. Here we have x cubed y over z to the negative 2, and it's all raised to the negative 1, and that's multiplied by z to the 4th. So again, let's try and eliminate the negative powers first. Before we really get started, let's just get rid of all the negative powers. So let's start off with this z to the negative 2. As we talked about before, we can just move that to the top. So that becomes x cubed y and z squared. We just drop the negative. But that is raised to the negative 1 power. The whole thing is raised to the negative power. And we're multiplying by z to the 4th. So that basically means that this thing right here is all in the denominator. So I'm going to change this to 1 over x cubed y z squared. And that's going to take this negative power, and that goes away now. And then we multiply by z to the 4th. Now, I have purposefully written this in a nasty way, because what do you do with this z to the 4th? I didn't write it as a fraction. So there is an understood over 1 here. And if you want to think of it that way, that's great. You can do that. But what I like to do is I just like to think of everything as, is it in the numerator or is it in the denominator? Well, the z to the 4th, there's no division, so it's in the numerator. So this is z to the 4th divided by x cubed y z squared. It's the same thing. And then finally, well, I didn't write out the exact rule. There's another rule that I didn't actually write here, and that's that if you have x to the n divided by x to the m, that's equal to x to the n minus m. Now, why didn't I write that? It's because you don't actually need it, and I don't like memorizing extra rules. So while this is true, and a lot of textbooks would show you that and say that's what you need to memorize, I don't like it. Instead, I'm going to put these in the same place. So I'm going to say this is z to the 4th times z to the negative 2. I know we're kind of going backwards, kind of getting rid of putting our negative power in, but now we can directly use this rule so that we don't have to memorize this last one. And it basically says that if you divide, instead of adding, you subtract. So if you want to just remember, if you just remember that division gives you subtraction, however you want to do that. But in any case, we say 4 minus 2, so 4 plus negative 2 is 2. So we have z squared over x cubed y. So that's how I would simplify this thing. That's quite a bit simpler than what we started with. I do have one more example, so let's do that. So now it's getting a little more complicated. We have z to the negative 1, x to the 4th over x cubed, x to the negative 2. And that's going to be divided by x cubed, z to the negative 2 over x. Whew. All right, so earlier I said let's start by eliminating the negative powers. And if you want to do that, go ahead. But one of the things I love about math is there's so many different ways. Pick and choose. I'm probably not going to do this problem the same way twice. So what I'm going to do, I'm actually going to just ignore these negative powers and say, I don't care. Instead, let's simplify a little bit. So this x cubed times x to the negative 2, that's just x. And when I do this x to the 4th divided by x, remember we're going to subtract those powers. So we get power of 1, so 4 minus 1 is 3. So this first fraction is just z to the negative 1 times 3. Oops, why did I say 3? Nope, it's x to the 3rd. Now I'm going to divide. This is just a real quick reminder, hopefully you remember, but when you divide a fraction, that just means flip it and multiply. So I'm going to multiply by flipping it. So x over x cubed z to the negative 2. Now I could have probably simplified this before I did it, but oh well, I didn't do that. Doesn't matter. So this becomes an x squared in the bottom. Notice that you subtract the powers, and whichever one's bigger is the one that wins. So the x cubed is bigger than the x, so we're going to keep that x squared in the denominator. So again, I'm going to think of this. We could think of it as, hey, this is over 1 and multiply across. But instead, I like to just think of what's in the numerator. We have a z to the negative 1, which, yes, technically, we could get rid of the negative power and move it to the denominator, but I'm not doing that right now. X cubed. And then we have this other x from the other fraction in the numerator as well. Oh, sorry. I apologize. I forgot. That went away. We don't have that x anymore, right? So that's all that's in the numerator. And then we have this x squared from the second fraction, x squared. And then we also have that z to the negative 2. So let's go ahead and simplify this further. So I'm going to move this z to the negative 2 to the top and become z squared. Times the z to the negative 1, well, that's just simply z. So that x squared is kind of in my way, but let's just call that z. And then for the x's, we have x cubed, and we'll subtract the 2, so x to the 3 minus 2 is just x to the 1. So this is just xz. That's all we have left. So I would say that's everything you need to know for calculus for your exponents. So let's go ahead and go on to the next topic. Let's talk about logarithms. So logarithms are basically the opposite of an exponential. In fact, that is how they are defined. I think that everybody defines logarithms just a little bit differently, but I think the definition of what is a log is an equation. If you have log base b of x equals y, that means the exact same thing as b to the y equals x. These two things are exactly the same thing. So often people ask me, well, what is a log? And that's my answer. It's kind of confusing because most things have kind of a more direct definition than this. But a logarithm is basically just the opposite of an exponential. So let's take a look at an example here. Or actually, sorry, before we do that, let's throw in some more rules that we can use. So if I have the log base b of a times b, we can break that up through addition to be the log base b of a plus the log base b of b. And if you have the log base b of a divided by b, then they're going to be subtraction. So it's log base b of a minus log base b of b. And I actually like to think of these as just one combined rule that when you split up logs, it doesn't matter how many there are, could be 2, 3, 4, 10, 100 different things that are multiplied and divided. Anything in the numerator gets a plus sign as you break it up, and anything in the denominator, which in this case is just this b right here, gets a minus sign. So I don't really think of these as just those two limiting rules. I think of it as all one encompassing rule. But you don't have to worry about that. Whatever works easiest to you is fine. So the next rule is the log base b of x to the n is equal to n times the log base b of x. Basically, this one is the most important one. It says you can take a power and move it out front to get that. So this is why we want logs, is because we can take a power and move it out front. Now, there are other rules that you probably learned in your logarithms class, but these are the most important ones because all the rest, well, they can be derived from these. So let's take a look at an example of something we can do with a log. So if I have the log base 2 of 8 equals 3. This is just a true statement. But what does it even mean? Kind of in the thought of what is a log? Well, if I look at this in terms of this definition, log base 2 of 8 equals 3 means that if I take the base, which is 2, that is this part, which is this one. So I'm going to take 2 raised to the power of what's on the other side here, that's the y or the 3, equals the stuff inside. So the 8 is the x. So saying that log base 2 of 8 is equal to 3 is exactly the same thing as saying 2 to the third is equal to 8. They're both true. It's just you're probably more used to seeing this form. So that's what makes logs confusing, is that you're just not used to it. However, it's really no different. So these two things just simply mean the same. Okay, let's take a look at another example though. But if we have the log base 2 of x is equal to 5. Now this is going to be pretty tricky. Like, what? We want to solve for x, but we have this in what's called logarithmic form. This is logarithmic form. Let me circle that in red. That is logarithmic form. If you have a log in there, it's logarithmic form, right? Well, you can also have exponential form, which means the same thing. Sometimes one definition is a lot easier to solve for x than the other, and I think this is no exception. So let's just convert this into exponential form and see if that makes more sense. So I'm going to take the base, which is 2, raised to the y power, that's 5, will always equal the stuff inside the log. So these two statements mean exactly the same thing. But hey, we can figure out 2 to the 5th, right? That's just 32. So x is equal to 32. So the only thing we had to do here is convert it from one form to another. Anytime you have a variable inside the log, well, this is the wrong form. We really should be using exponential form. So all you have to do is just convert it. Let's take a look at another example. Let's go ahead and start this with a new example. We have the log base 3 of x is equal to 1. Now again, I need to find x, but this is in the wrong form because we have x inside the log. So I'm going to take the base to the y power is equal to the stuff inside. Well, x equals 3 to the 1, so x is equal to 3. If we can convert between forms easily, it's very easy to actually figure this out. Okay, let's take a look at another example. Here we have log base 2 of 1. It's not equal to anything. We just simply want to simplify it. So how can you figure this out? Well, how about we just set that equal to y? And if we can figure out y, then we can figure out what log base 2 of 1 is, because they're the same thing. So what I'm going to do here is convert. I know I said before that anytime you have the variable inside, that's when you want to switch to exponential. But there's exceptions to every rule. And I think you'll see why here. If I convert this, I'm going to have the base to the y power is equal to the stuff inside the log, which is 1. Now, this doesn't directly help us, but it might help us understand what does the log base 2 of 1 mean. 2 to what power is going to give you 1? Well, anything to the 0 power is 1. So it's 0. That means log base 2 of 1 is equal to 0. And in fact, there's another rule that sometimes people would give you, and it says log base b of 1 is equal to 0. I don't care what the base is, the log base b of 1 is 0. And if you want to, you can go ahead and just memorize that. However, I don't like to memorize. I'd rather just solve it. But it's up to you. You can memorize this as a formula or not. Okay, let's look at another one. Here we have the log base 2 of 2. Okay, I'm going to do basically the same thing I did before. Let's set that equal to y and say 2 to what power is equal to 2. Clearly, that's going to be 1. Right? So log base 2 of 2 is 1. And again, this is one of those rules that you might have memorized, is the log base b of b is always equal to 1. And here's your reason for it. But again, I don't necessarily say you should memorize it. I just figure it out from the original rules. But that is entirely up to you what you want to do. Okay, let's go into some other ones. Let's look at the log base 2 of x times 4. Now here, there is no x inside, and except in those rare situations, I think switching between forms is only useful if x is inside the log. So instead, we have two things multiplied together. So it seems like we should use that rule, right? So that would be we have log base 2 of 8 plus log base 2 of 4. Remember, things that are multiplied inside the log become addition outside the log. But then we have another problem. Well, we have an 8 here. So oftentimes it's a good idea to change this into an exponent inside the log. So that 8 I'm going to write as log base 2 of 2 cubed. That 2 cubed is equal to 8. Plus we have log base 2 of 2 squared. And now I can make use of the last rule here, that if I have a power, I can bring it out front. So I'm just going to take this 3 and move it out front. Same thing with this 2 and move it out front. Multiply. So I have 3 times the log base 2 of 2 plus 2 times the log base 2 of 2. Well, remember from the last part, log base 2 of 2 is 1, so we can just ignore that. 3 plus 2 is 5. So this is equal to 5. Now, with math, there's always all sorts of ways to do it. So I'm actually going to point out another way we could have done this. Let's, instead of taking this 8 times 4 and breaking it up, how about we just say, 8 times 4 is 32. So take the log base 2 of 32. And 32 is actually 2 to the 5th. So this is log base 2 of 2 to the 5th. So now we can use that same rule and take the 5 out front and multiply by the log base 2 of 2. And hey, we still get 5. They're both the same. Either way you do it, it's 5. Let's take a look at another one. Let's say we have the log base 5 of 25x. And what we want to do here is just simplify as much as we can. So what I'm going to do is I'm going to notice we have multiplication here. So we can use this rule. Add them up. Log base 5 of 25 plus log base 5 of x. Now this one is as simplified as you can get. There's just nothing there that can be simplified. But this one, well, 25 is 5 squared. So we have log base 5 of 5 squared. We can take the 2 out front times the log base 5 of the base, which is 5. Well, that's just 2, because this thing is 1. So this is 2 plus the log base 5 of x. So that's as simplified as this can get. All right, let's do another example. Let's simplify log base 2 of 64 over 4. Now here we have division. So we can use this rule that says that, hey, if it's in the denominator, it gets a subtraction sign. So we have log base 2 of 64 minus now log base 2 of 4. But if you take a look at 64, let's see, that is 2 to the 6th. So we can bring the 6 out front times the log base 2 of 2 minus, well, we have 4, that's 2 squared. Bring the 2 out front times the log base 2 of 2. But again, log base 2 of 2 is 1, so it doesn't really affect anything. 6 minus 2 is 4. And again, I want to point out we could have simplified 64 divided by 4 is 16, and 16 is 2 to the 4th. So, hey, same answer. Many different ways to do it. All right, let's do something a little bit different, but still involving logarithms for the next example. Say we have ln of x plus 1 is equal to 0. Now, I haven't talked about this, but ln is just a special log base. It's base e. It's called the natural log, and I won't get into too much about what e is, but it's a constant. You use it a lot like you would use pi. It's a very different number, right? E is about 2.71828 is what I have memorized. You can type it on your calculator if you want more information. It's an irrational number and it's a constant. That this just means log base e of x plus 1. Anytime you see ln, it just means log base e. Now, one thing I don't understand, if anybody knows, let me know in the comments, but I don't know why we call it ln. I'm guessing it has something to do with Latin or some other language, but seems like natural log should be nl. Why is it ln? I don't know. But that's what it is. We call it ln. So, knowing that that just means log base e, to solve this equation now, we have x inside the parentheses. So that means let's switch over to exponential form to try and solve for x. So I'm going to take the base, which is e, to the y power, is equal to the stuff inside the log, x plus 1. Now we know that anything to the 0 power is 1. So we have 1 is equal to x plus 1. Subtract 1 for both sides, we get x equals 0. So if x equals 0, that's the solution. We can plug it in to find out, and notice that the ln of 1 is what we would end up with, which the ln of 1 is 0. So that does work out. Okay, let's look at one last example for logs. Here we have the log of x squared is equal to 2. Now, I did not write a base at all. So if you don't write a base, it's an understood 10. So this means log base 10 of x squared is equal to 2. To solve it, notice that x is inside the logarithm, so we're going to swap over to exponential form. So that means we take the base to the y power, the stuff on the other side. So 10 squared has to equal the stuff inside the log, x squared. So that means x squared equals 100. We'll take the square root of both sides, meaning we have to do plus or minus anytime you do a square root. So 10, because that's the square root of 100. So now we've covered what I believe to be the main important topics for logarithms before you take calculus. If you understood everything here, I think you're good to go on logarithms to take calculus. So let's go on to the next topic. Let's talk about transformations, specifically for graphs. So let's say we have y equals x squared as a basic example. Let's go ahead and graph that. And it's going to look something like this. It's a parabola that opens upward. Now I do want to point out, please make sure you do know how y equals x squared looks. You will need that for calculus. But we will talk more about polynomials in general and how to graph them a little bit later. So don't worry too much about it just yet. So for shifting, what if I take that graph and then I'm going to say y equals x squared for the next one, but instead I'm going to say minus 1. Just at the very end of this thing, I'm going to shift it down. Well, I just go down. So I just go down 1. So now at this point, every point on the graph will get moved down 1. So it doesn't actually change the shape of the graph at all. It looks exactly the same, except it's just been moved down 1. Another thing we could do is we could shift on left and right. Oh, before I go into that, I should point out this minus 1 moves it down, but a plus 1 would move it up. So like if I did a plus 1, it'd look like this. So you just move up and down however that ending thing is. Now, let's go ahead and take a look at what if I did y equals x minus 2 squared minus 1. You'll notice I still shifted down 1 here, but now I'm doing an x minus 2. Now, this is backwards from what most people think. So this minus 2 actually moves to the right. So I'm going to take this red graph that I had before, and I'm going to move it to the right 2. The minus sign means right. If we did an x plus 2, that's what would move it to the left. So that's how you shift left and right, is inside the parentheses. I often say that things inside parentheses are opposite what you think they are. It's a kind of a general rule that applies in most of math, but it's certainly not a overarching always rule. So x minus 2 squared, then, is going to take this point here that we got from the red graph that shifted it down, and now I'm going to move it to the right. So this point right here is going to be 2 over. So we went down and over 2 is what shifting did. And then otherwise, just like before, this graph isn't any different. It has the exact same shape as before. Nothing is different except just where it moved. The vertex right there has moved over, and along with every other point on the graph. There's one last thing that we can transform with, is what if I did like an a value? So I have 3 times that x minus 2 squared minus 1. So in this case, it looks exactly like the green graph, but this 3 here is going to just change it vertically. It's going to make the whole thing steeper. So it's not going to change where the vertex is, but it's going to be just a little steeper. It's going to look like this. Now, there are several versions of what this a value could be. Here, like say if we had a negative 3, then we would make it like this. Or maybe we had it be a negative 1/3. Well, if it's less than 1, it's going to expand it out like this. So there are a few different versions of what the a value can do, but that's generic what it does in general. Now, one thing I want to point out that I don't think gets emphasized enough when you learn these things initially is what I have been talking about is not unique to quadratics. Not at all. Some people would tell you, okay, y equals a times x minus h squared plus k. That is the generic form. It involves everything we've talked about. K is the up and down shift. H is the left and right shift, and A is the kind of like the slope. It gives you the steepness. And while that is true, any function I give you would be basically the same thing. For example, let's take this graph of f of x. It's some random who knows what graph. It's certainly not a quadratic. But if I wanted to say what is the graph of f of x minus 1 plus 3 look like? Well, this is the shifting of x, and this is the k. So basically, what this graph is going to do is it's going to move everything to the right 1, and it's going to move everything up 3. So this new graph let's start with this point. It's going to move from that point there. It's going to move to the right 1. So I guess it started off over here and moves over here, say, wherever that 1 is, and then up 3. So that point is right here. But otherwise, everything's the same. Goes through, looks the same. It's just been moved over to the right 1 and up 3. Any function at all follows these exact same transformations. So in algebra, they teach you a lot of transformations for each of these graphs, but it's all the same stuff. What you learn for one is the same exact thing for the others. There just might be different notation and things, but pretty much it's all the same thing. So let's go ahead and go on to the next topic. Now we'll talk about polynomials. Polynomials are basically the typical shape and graph that we like to talk about. In fact, we convert other things into polynomials sometimes. You'll learn all about that in calculus. But basically, a polynomial just means you have x to a positive power. Actually, a positive whole number power. So like, for example, if I have x cubed plus 3x squared plus 6, that's a polynomial because each term is raised to a positive whole number power. Whereas if I have like x to the 1.5, that's not a polynomial. Or x to the pi, that's not a polynomial. It has to be to a positive whole number power. So like -2, nope, not a polynomial. Okay? So now that we know what polynomials are as a quick review, let's talk about what they look like. What is their generic shape? Because in calculus, you will not necessarily have to know their shape, but it makes the question significantly easier. So we'll start off with y equals x squared, which we already looked at in our previous section, but it looks like this. That's x squared. Now it turns out that any even power pretty much looks the same thing. Y equals x to the fourth is just going to be basically the same thing, but it's a little flatter. So it just kind of comes down here and it comes a little flatter like this. But you're not going to notice that much difference. If I were to do y equals x to the sixth, for example, well, it's just going to be even more so. Something like that, right? And if I were to do like y equals x to the 1,000th, well, that's pretty much just going to be straight up, straight over, straight up. It's like, looks very, very boxy. However, if you zoom in here, you'll find that it actually does have a curve. So really, all of these graphs pretty much look the same. There's not much difference. But that's the even ones. The odd ones kind of follow the same pattern. So if we look at y equals x cubed, it looks kind of like a double parabola, right? Like it's upward on one side and downward on the other. If I will look at y equals x to the fifth, just like before, let's make that one in red. Just like before, that kind of just makes it a little more steep. But it pretty much looks the same. And if I were to do like say y equals x to the 1001 power, it would be very straight. Looks very similar, just higher powers. That's all it does. So now we kind of know how to graph a polynomial, or at least these very simple ones. But what do you do if it's a mixture between other polynomials? For example, this polynomial. We have x to the fifth plus 3x to the fourth minus 8x cubed plus x squared plus 1. Oof, that's nasty, right? What does that graph look like? Well, it turns out you don't really need to know everything. All you need to know is the highest power. This is going to look very similar to an x to the fifth graph. which if you remember looks a lot like an x cubed graph. Looks like that. Now, these middle terms here, these ones, do some funny business that I'll talk about in a bit. And this plus 1 just moves the whole thing up 1, just like the transformations we've talked about in the past. Now, what these middle terms do is they dictate what happens if you zoom in. So it's not going to actually look like this graph. If I zoom out, it will. But if I zoom in, it's going to look something like this. I don't know, something like that. I call these things just wiggles. There's some ups and downs that happen in the middle. And that's what these things dictate. Now in calculus, we'll start to be able to determine exactly what those things do. But for now, just know that they affect the wiggles. They affect how much it wiggles in the middle. In calculus, though, I will point out that the first one that we have is going to be a maximum. That point is the first maximum. And then we'll have a minimum, and then a maximum, and a minimum, and a max, and who knows how many. But it'll go in that order for the most part. We'll talk in calculus a little more specifically about how what I said isn't 100% right. But now we know kind of what a fifth power looks like. It doesn't matter what all these lower order terms do. We know pretty much what this looks like. And note, the same is true if I were to take out this fifth power, then it would look like the next highest power, which is a quartic, which would make it look like this overall. But it'd have some wiggles in the middle. All right, so now I think we know everything about polynomials. So let's go ahead and go on to the next section. This section is about linear equations. So a linear equation is basically just a straight line. You could think of it as a polynomial of degree 1, but it's kind of separate, so it's going to have its own section. There's a lot more we can talk about with linear equations. So I think the most known equation is y equals mx plus b. This one is very useful for finding an equation of a straight line. But there are other equations you definitely are going to want to know as well. Y equals y naught plus m times x minus x naught. That's an equation that I think you'll want to know for calculus. And also m equals y2 minus y1 over x2 minus x1. So these three equations will definitely be needed in calculus, especially early on in calculus. You'll be doing a lot of this, like a lot of this. It comes up a lot. I can't say that word enough. So how can we actually use these equations? Let's start off with an example. So let's find an equation of a straight line that goes through the point 2, 4 and has a slope of 5. Okay, we want to find an equation that goes through this point and has that slope. We could graph it just to kind of see what's going on. 2, 4, that's at 2, 4, so like right here, and it has a slope of 5, something like that, right? But what's the equation? Now, this first one is often called slope-intercept form. It's very useful if you know the slope and the intercept, which we do not here, right? We know the slope, but we don't know the intercept, so I would not use this equation. This second equation is called point-slope form because it's great if you know a point and you know the slope. Well, hey, we know a point and we know a slope. So this equation is what we want to use. So y naught means the y value of the point and x naught means the x value of the point. So we can just plug it all in. Y equals y naught, well, that's 4. That's the y value of the point, right? It's the second value in there. Plus m, which is 5. They directly told us that. M is the slope. Times x minus x naught, which is 2. We're done. I would say, and most of the time in calculus they say the same thing, but usually you don't have to simplify because it can get complicated if you simplify. So I would just turn this in and say, hey, that is my answer. However, if you're asked to simplify, all you have to do is distribute the 5 to get 4 plus 5x minus 10. That's the 5 times negative 2 is to negative 10. And then combine to get 5x minus 6. 4 minus 10 is 6, negative 6. So 5x minus 6 is the same thing. All we did when we simplified is we took this equation that was in point-slope form and we converted to slope-intercept form. But they're both equally correct. Do whichever one you want to do, unless your teacher tells you otherwise. They mean the same thing. Okay, let's take a look at another one. Here, we're going to ask for the same thing. Find the equation of a straight line that has a y-intercept this time of 2 and a slope of negative 2? Well, in this case, we were told the y-intercept and the slope. So that makes sense to use the slope-intercept form. So I'm just going to say y equals the slope, that's negative 2 times x, plus b. Well, it was fast and easy, right? If you graph this, it has an intercept at 2 and it has a slope of 1. There's the equation of that line. All right, let's do another one. So again, we want to find an equation of a line, but this time we want to find one that goes through these 2 points, 1, 3 and 2, 4. Now, if I look at these options here, this one is only good if we know the intercept. So I'm not going to want to use that, right? This one is only good if we know the slope and a point. Well, we only know 2 points, but we don't know the slope. Well, luckily, we have another equation. If you have 2 points, you can find the slope. So after a bit of calculation, we will know the slope. So we're going to then still use the green equation, which is the point-slope form. But first, we need to find the slope. Now, the y2 minus y1 over x2 minus x1, I think of it as just change in y over change in x. So what I like to do is I'm going to label this 0.1 and I'm going to label this 0.2. It really doesn't matter which one you do. If you label the first one 0.2 and the second one 0.1, you'll get the same answer, which is kind of interesting. But y2 is just going to be the y value that is on 0.2, so 4. And y1 is going to be the y value on 0.1, so 3. And then we'll divide by, same idea for x. We have x2, which is 2, minus x1, which is 1. So then that's 4 minus 3 is 1 over 1. So the slope is 1. Now, I mentioned earlier that you can do it the other way around. What if we did that? What if we swap P2 and P1? If we did, then we would have 3 for the y2 minus 4 over 1 minus 2. We would just flip everything. But then we would get negative 1 over negative 1, which is still 1. So that's why it doesn't matter. However, I want to point out, and this is something people miss a lot, so be careful. You have to keep it straight. What would be wrong is if you flipped part of a point. Like if I did 3 minus 4 divided by 2 minus 1, that would be, I flipped the x's but not the y's. I didn't keep it straight. So this is going to be negative 1, which is wrong. Don't do that. So label your P1 and P2 and then keep it straight from there. But it really doesn't matter which one you choose. Okay? So let's back up to where we have the slope. We don't have to compute it multiple ways. We know the slope is 1. So now we know a point, actually 2 of them, and the slope. So I'm going to say y equals y naught. That's the y value of a point. Well, which one do you want to use? It doesn't matter. You can use P1 or P2. You pick. I'm going to choose the one with the smaller numbers. I'm going to use P1 here. So y naught is 3 plus m, we calculated that is 1, times x minus x naught. So again, like I said before, I would just say, hey, that's my solution. However, if you want to simplify, that's fine. We distribute the 1, which really means just drop it. So 3 plus x minus 1. So that becomes x plus 2. Same equation, same answer. All right, let's do another problem. So here, we want to do basically the same thing. But we want to find an equation of a line through negative 1 comma 2 that is parallel to the line y equals 2x plus 6. So this means we have to know what parallel means. And I want to point out that this problem right here is exactly the problem you definitely need to know before you take calculus. You will be answering questions very, very similar to this, just with a calculus spin on it. So what we need to do is first note, what does parallel mean? It means the same slope. That's what parallel means. It will have the same slope as this line here. Well, if you look at this line, it's in mx plus b form, so the slope is 2. So when I said parallel to y equals 2x plus 6, that means the same thing as saying the slope is 2. So we know how to do this from earlier. It's the same problem we did over here. We'll use this equation. We have y equals y naught, that is the 2 value here, plus m, which we found to be 2 from this slope here, times x minus x naught. Minus a negative means plus 1. And I'm done. Although, if you want to, we can simplify it. 2 plus 2x plus 2 is 2x plus 4. That's it. So there's one more example that I do want to point out that they can do that you should know about. And that's going to be, instead of parallel, let's say it said perpendicular. I don't know how to spell it. I'll just call it perp. So find an equation of a line that's perpendicular. Well, this would be a little bit different because what we would do is do -1 over the original slope. A perpendicular line has a slope that is -1 over the slope of the other one. So the slope would be -1/2. Otherwise, it's the same thing. We'd still have y equals y naught is still 2 plus m, this time it's -1/2 times x plus 1. Nothing changed. I'll let you simplify that if you'd like. I'm not going to bother because, like I said, I think that is the correct answer. It doesn't need simplified any further. So now we know how to do linear equations. So let's go on to the next topic. We need to know about substitution. Substitution is basically the way that you solve problems, for the most part. Now, it basically says that if one thing is equal to something, we can just plug it in anytime we see it. So for example, let's say we have y equals 2x plus 3. But we are also told that 2x minus 5y is equal to 4. Notice that we have two equations and two variables. That is the case that we want. If you're given the same number of equations as variables, that means we can go ahead and actually solve this. We probably, although not definitely, but probably can get a unique solution. So substitution says that, hey, y is equal to 2x plus 3. So everywhere we see a y, let's just replace it with 2x plus 3. So in the second equation, I'm going to have 2x minus 5 times y is equal to 4. But I'll replace y with that 2x plus 3. We can do that because, well, y is 2x plus 3. It's the same thing. So now we can continue simplifying. I'm going to distribute the 5. So 2x minus 10x minus 15 is equal to 4. And continue solving. So 2 minus 10 is negative 8x. I'll add 15 is equal to 19. So that means that x is going to be, if I divide by negative 8, 19 over negative 9, or 19 over negative 8. So we found x. So now that we know x, we can easily find y by just plugging that in here, because x is 19 over negative 8. So y is going to be 2 times that plus 3. Which, yeah, sorry, I should have chosen ones with a little nicer numbers, but that's okay. Let's grab my calculator and plug it in. That gives me negative 7 over 4 for y. So this is substitution method. This is the substitution method for solving equations. Now, in algebra, you learned also elimination, but I'm going to tell you right now, it really isn't important. At least not for Calc 1. There are times if you get into past Calc 1, get into like linear equations, then yes, elimination is important. But for calculus, I don't think we need to worry about that, so I won't be covering it here. If you'd like me to cover it in depth, please let me know in a comment, and I will be happy to do that in a future video. But for now, let's go ahead and look at another example of substitution. This time, let's say we have x minus y equals 1 and x plus y equals 2. So in this case, it's going to be a little more tricky because we don't have it solved for any one of the variables. In fact, this is one where elimination method might actually be the right choice. However, you never really need elimination, so I'm just going to do substitution anyways. So using substitution, it means let's take one of these equations and solve it for one of the variables. It doesn't matter which equation, and it doesn't matter which variable. But I'm going to take the first equation and solve it for x, just because I think it looks easy. That's the only reason. So I'm going to add y to get x is equal to 1 plus y. So I'm just going to use that instead of what was originally here and just ignore that equation. So I'm going to take that 1 plus y and plug it in for x because, well, x is 1 plus y. So I have x, which is 1 plus y is equal to 2. So that's 1 plus 2y is equal to 2. Again, we just solve. So we'll subtract 1 to get 2y equals 2, or y equals, that's 1y equals 2. So, sorry, I don't know what I'm doing here. 3y equals 2. Wait, I'm just being completely wrong. Sorry, just a sec. I'm going to subtract 1 to get 2y equals 1. Sorry about that. And then I divide by 2 to get y equals 1/2. So we know y equals 1/2, so plug it back into what x is. So x is going to be 1 plus 1/2, which is 3/2. So that is substitution. So this is very important, not necessarily for being able to solve equations like this, but for other reasons. In calculus, we're going to do substitution by basically just using the idea that if x is equal to something, we can plug that in anywhere we want. And it'll be used in kind of a little bit different scenario than we are here. But if you understand this, you should have a you shouldn't have trouble in calculus with that part. All right, so this was actually our last section. However, a lot of people probably need a little more practice. So the next portion is just going to be examples. The first example that could include everything that we've discussed previously is to simplify and graph this equation, x squared minus 4 over x minus 2. So go ahead and pause the video, give this a try on your own, and then come back and see how you did. All right, let's see how you did. So to simplify this, what I'm going to do is factor everything. Whenever you have, this is what's called a rational expression. If you have a polynomial divided by a polynomial, it's a good idea to factor it because we can tell a lot from what's going on with a factored equation. So x squared minus 4 is the difference of two squareds, factors into x minus 2 times x plus 2. And then that x minus 2 doesn't matter, right? Well, then we have these things factored, which means now we can cancel them out. So we get x plus 2. So let's just graph that. We can think of this as mx plus b form. The slope is 1 and the intercept is 2. It looks like this, right? Wrong. Haha, I got this wrong. Hee! What did I do wrong? I'm very, very close. But in actuality, this to here is wrong. These two equations are not the same. You can find out by saying, well, if they're the same, that means that x is this, you get the same value for all x. But what about if x is equal to 2? If x is equal to 2, we get 4, right? That's like here. But if you look at the beginning, what if x is equal to 2? You get 0 divided by 0. So these are not the same. So to make it right, to just fix everything, let's just say x is not equal to 2. Whenever you cancel like this, you're assuming that x is not equal to that denominator. As long as it's not, then you can do that cancellation. So I'm just going to say this is true as long as x is not equal to 2. Now I got it correct, but I need to have an open circle here. So my graph is x plus 2 as long as x is not equal to 2. If x is 2, there's just no value. It doesn't exist. All right, that was a bit of a trick question there. So let's go on to the next one, though. Here, I want you to simplify x, let's put it in black, x divided by the square root of x plus 2 minus the square root of 2. Let's see if we can simplify this. Now, warning, this is introducing a new topic that I haven't discussed, but give it a try anyways, and then we'll talk about it. All right, let's see how you did. So what we need to do here, if you have a square root that you need to simplify, is multiply by the conjugate. The conjugate just means flip the sign. So I'm going to multiply by the square root of x plus 1, or sorry, x plus 2 plus the square root of 2. I just changed the sign here. But to do that, I better do on top and bottom, so that I didn't actually change anything, right? You can multiply by 1 and nothing changes. So on the top, we have x times the square root of x plus 2 plus root 2. There's really no reason to do anything else there. Let's just leave it at that. On the bottom, we need to FOIL it out. However, when you multiply something by its conjugate, you're just going to get the first term squared minus the second term squared. So we'll just get the square root of x plus 2 squared is just x plus 2 minus the second one squared, so the square root of 2 squared is 2. Now, I didn't show it, but feel free to write out the foiling if you need to and, distribute that and FOIL it out. But you should get what I got here. So now the 2 minus 2 goes away. So this is just x times the square root of x plus 2 root 2 all over x. So we can cancel out the x, assuming x is not equal to 0, right? And then we get the square root of x plus 2 plus the square root of 2. That is only assuming x is not equal to 0. Now, this is very useful in calculus. We will be doing a lot of these for something called a limit. We're going to take a limit, which will require us to simplify in ways very, very similar to this. All right, let's take a look at another example. Here, we're given a function f of t, which is t squared plus 2. And we want to find f of 1 plus h minus f of 1 over h. Now, yes, I did already do some examples like this before. However, this is a very important topic for calculus, so I just wanted to stress that we do know how to do these. So go ahead and pause the video and see how you do. All right, let's take a look. So what I'm going to do is start off by finding f of 1 plus h. That means we're just going to take that t squared plus 2, and anywhere we saw a t, we're going to replace it with 1 plus h. Now, we need to FOIL out this portion, which means we're going to square the first plus square the second plus 2 times the 2 multiplied together. If you need to, go ahead and write out the 1 plus h times 1 plus h and FOIL it. Either way, you'll get the same answer here. And then we just add on that 2. This gives us 3 plus h squared plus 2h. And then we need to subtract the f of 2, or f of 1. Well, f of 1, if we plug in 1, we get 1 squared plus 2 is 3, all over h. So now the 3 minus 3 goes away. We have h squared plus 2h over h. We can factor out an h, divided by h, and assuming h isn't 0, we get h plus 2. So our answer is h plus 2. Now you might ask, why did I not bother saying h is not equal to 0? I probably should have, actually. However, we usually don't in these cases because when we look at this in calculus, we're actually taking what's called a limit, which by definition says that h can't be 0. So we really don't need to do that in calculus. However, since we're in algebra, we haven't learned that yet. So I really should be saying h is not equal to 0. Let's take a look at one more example. Here, we're given a function, f of x, which is equal to x squared plus x over x plus 1. And what I want to do is find the zeros and find where is it undefined. So go ahead and pause the video and give this a try. All right, let's take a look, see how you did. So to find the zeros, we actually just need to set the numerator equal to 0. So to solve that, I'm going to factor out an x. We're left with x plus 1. And we're going to get x equals 0 or negative 1. So those are my zeros. Or are they? Turns out it's not quite right. Okay? So before I explain why, let's go ahead and look for where it's undefined. So it's undefined if the denominator is 0. X plus 1 equals 0. We get x is equal to negative 1 is where it's undefined. Now this, I think, if you take a look at it, really tells why the 0 wasn't right. Because it is undefined when x is equal to negative 1. How can it be undefined and 0 at the same time? Turns out that if x is equal to negative 1, we get 0 divided by 0, which is undefined. So to find zeros, what we really need to do is find the places where the numerator is 0, but the denominator is not. So basically, whenever you're finding zeros, I would just go ahead and find out where is it 0 and where is it undefined. Just go ahead and find them both. And if it's undefined, it can't be 0. So here, our only answer for the zeros is x equals 0. So it's 0 at 0, and it's negative 1 is where it's undefined. All right, this was our last example. So if you followed this entire video, I think that there's a very good chance that you are ready to take calculus. If you think I missed any subjects or you have any other questions, feel free to let me know in the comments. I'd be happy to take a look and maybe make another video about it or just reply in the comments. Also, be sure to like and subscribe to the channel so you don't miss out on any other good math advice.